Alright, the purpose behind this set of notes is to get you guys started with Unit 7 a little bit quicker than we would normally be able to. A lot of this is going to be coming from your textbook, and it might actually help you with the reading note quiz that you guys have. What is that? Due Thursday, I believe it was. Don't quote me on that. It's on your calendar. But this is meant to be a quick overview of that material that came from the chapter in the book that we're talking about. So this is going to be over mostly what we're talking about right now is Newton's universal law of gravitation. Assignment 2 is going to touch a lot more on Kepler. The book and the reading notes discuss a lot of Kepler. And so that's going to be something that we come back to and definitely use and apply, not so much in terms of mathematics, but just conceptually. So recall first and foremost that forces, what we literally just got done talking about in Unit 5, forces are anything that cause objects to accelerate. Right, so they cause an accelerate. Let me actually write out what that word should be so that it fits. Forces are anything that cause an acceleration. Right, that acceleration could be speeding up, positive, or it could be negative, and you're slowing down, or it could be a centripetal acceleration. This year, because of all the crazy COVID stuff that was going on, we didn't get a good chance to talk too much about that change in direction, but we're definitely going to be using it here, at least at the beginning, conceptually. We're not going to be doing the mathematics for centripetal accelerations and centripetal forces, even though it's still just for a force, it's F equals ma. But we're not getting into that too much. We're going to touch on it very briefly conceptually. But a centripetal force, and this is one of the vocab terms that we are going to need to know, is a change in direction. Right, so that's our third way that an object can accelerate: speed up, slow down, or literally turn. We notice this all the time when you take a sharp turn into your neighborhood. The stuff on your dashboard might go sliding one direction or the other, or when you are, on your entrance or exit ramps on and off the highway. Things in your car slowly begin to shift to one side the longer you're making that turn. That's an example of a centripetal force causing a centripetal acceleration. It comes back to inertia. Objects don't want to change what they're doing, and when you make them change direction, they're going to resist that a little bit. And that's what you notice inside your car when you're making those sharp turns. These centripetal forces can be a result of a number of different sorts of actual forces that we would describe using vocab terms. They could be anything from tension on a string, as you're swinging a yo-yo around. We didn't get a chance to do the pig lab because we skipped over the centripetal part of this, but you could envision someone like twirling their keys in their lanyard, right? Maybe you'll catch a coach outside in the spring doing something like that, right, where they're just standing there spinning their keys. That's a good example of tension, or a yo-yo, or anything else like that. You could also have friction. Friction's the one that you're most familiar with, right? You've got to have friction between your tires and the road in order to make that turn. If on a cold, wintry day where there's a lot of ice, you try to make that turn and there's not enough friction, because we just got done talking about that coefficient of friction. So if that value gets too low for your coefficient of friction, then there's not enough friction to force you, literally, to turn that direction, change your direction, and you're just not going to. You're going to go sliding. Again, inertia, tendency for an object to keep moving in the direction that it's moving. Or, this is the most recent one, this is the one we're going to be talking a lot about in this unit, is obviously gravity. Gravity can act like, basically, it's almost like a string, pulling things, closer to its center. And that's what we're going to be referring to as the primary, I guess you could say, force that is causing this circular motion of these planets and different satellites and things like that orbit one another when we talk about gravity. Now, gravity is going to be an attractive force. It's kind of like mass. I haven't really heard of a good mathematical explanation why negative mass or negative gravity, anti-gravity can't exist mathematically. We just don't observe it or know how we could make something like that. It's just, if you do the math in certain ways, sure, it's a potential product of the mathematics. We just don't ever observe it, so we tend to gloss over it. But It's caused by objects containing mass, right? So everything that has mass is going to be able to exert some sort of gravitational pull. That's the only stipulation. You just have to have some version of mass. A single atom of hydrogen is going to have mass and is going to have a gravitational pull or gravitational attraction with nearby objects. That attraction gets larger the more mass you have. And we'll talk about that with our equation down below in a second. So they are proportional that way, but that atom of hydrogen is going to have a gravitational pull that it can exert on other things. That's just going to be a lot less than the gravitational pull, let's say, of the Earth, right? Because the Earth is significantly larger than a single atom, on the order of hundreds, if not thousands of billions of times larger. So, anyways, Newton actually came up with this relationship. Ironically enough, he derived this equation at one point in his life, didn't think much of it, and lost it. And then, like 5 years later, a few other people, Hooke and Halley and a few others, came along and were asking him, "Hey, can you help us with the mathematics behind this?" Because he had just invented calculus. And he's like, "Yeah, I did that a couple years ago. I don't know where it is. Let me just redo it for you." And he did, and here we are. Anyways, so the really complicated looking equation that we have here, one of the things that is always best, especially the further we get in this year, because this is the last unit of the semester. This isn't the last thing we're doing for the year. One of the things that is really, really, really good to do is going to be to not only write these equations out into words, but then also label what each part means, because right now R is new to you and a capital G is new to you. M1 and M2 you probably figure out. FG, I hope that looks familiar, but there are two new ones, and you need to know what they represent and what they mean so you know what numbers you need to be plugging in what location. Again, for the observations that Newton made a long time ago. So, the relationship Newton and his colleagues were able to derive observing planets orbiting the sun and things like that was that the force of gravity, or your weight, remember, your weight is a force of gravity, is directly proportional to the product of the masses involved, right? You're taking those two masses, M1 and M2, and you're multiplying them together, and is inversely proportional to the distance between those masses. And that's where this guy right here comes in. That's going to be your radius, the distance between the two masses. The reason we're interested in radius is if you look over here on this little diagram right here, the distance between the Earth and the Sun is actually going to have a few different points that I guess you could measure from, right? You could measure from the front of the Sun, you could measure from the middle of the Sun, or you could measure from the back of the Sun. But considering the Earth is going around it, the front and the back kind of become arbitrary, so we always measure from the middle. And that's why we use it as or describe it as the radius in our equations. It is your distance from the center of the object, and that's always what we're going to be using. So it's the center of the Sun to the center of the Earth, or if you wanted to measure your weight, it's from the center of your mass all the way to the center of the planet, and that's the distance that we're going to be using. So at some point, we are going to need the radius of the planet or the radius of the Sun, but those aren't numbers you have to memorize. Those will be given to you. So again, really good habit to get into. Describe these things. This is a force of gravity. We can also describe it as a weight. And it's going to be measured in newtons. Same thing it's always been measured in, right? And that's what I'm doing. The first line is what it is. Second line is what it's measured in. This is going to be, let's go with the next one that we should recognize. This is the product. We're multiplying them of the masses involved. So we've got M1 and M2. All right, if you want to talk about the amount of weight an object has or how much gravitational force two objects might exert one on another, then you need to know the mass of both of those things, the mass of you and the mass of the planet, or the mass of the Earth and the mass of the Sun. It just depends on which gravitational force it is that you're looking at. And of course, because this is a mass, these are going to be measured in kilograms. Always going to be measured in kilograms. R is our radius. It is the distance between the center of the mass of both of those objects, whatever they might be. And as usual with all of our distances, this is going to be measured in meters. Now the new one. Right, this is the one that a lot of people will gloss over in your reading notes, and this is definitely on that reading notes quiz. This is our universal gravitation constant. And because I use that word constant, it doesn't change ever. It's like pi. It's one of those things that the more they did these calculations and the more they tried to, take the observations, really is what they were doing, and fit a mathematical model to them, this is the number that they were off by every single time. And it's just one of those things that it popped up no matter what planet or star or moon or artificial satellite lately that we've been able to put up in orbit around the Earth or around any other planet. This value, kind of like pi did with our Circle Lab way back at the beginning of the year, this just keeps popping up again and again and again. And so we refer to it as a universal gravitation constant. Its value, because this is never going to change, is 6.67 times 10 to the negative 11th. Because it's a negative 11, you're going to take that decimal point in between those two sixes, and you're going to actually move it 11 spaces to the left. This is a really, really, really small number. So Newton wasn't off by much in terms of the mathematical model he tried to come up with in order to predict the motion of these planets and other things, basically anything that orbits something else. The units here are a little complicated, and we're not going to do too much with it. But I do want to point it out. Your units here are going to be a Newton multiplied by a meter squared per kilogram squared. And I bring that up only because if you look at the units of that constant, you've got kilogram squared in your denominator here with g, and kilogram squared up in your numerator with the product of those two masses. And so those will cancel out. And then in your denominator, you have your distance squared, and that's your meter squared. And they all cancel out one another, and the only thing you're left with is newtons, which is what your weight and your forces should always be measured in. So the units do work out. Super complicated and weird looking units, and you will see them on your cover page of your unit packets, but that's what it means. That's why they're there the way that they are. Now this I'm going to put a big star by, because this is the first time you've seen this sort of relationship, this sort of, how do I want to describe it, this sort of equation being used. And this is what we refer to as an inverse square law. And it's really complicated. No, it's not really complicated. It's really easy, but it's also one of the things that a lot of students just kind of gloss over and fly through, don't give much thought to it, assuming they're doing it correctly, because we just got done, doing our factor of change conversations with F equals ma, where nothing was being squared. Well, you'll notice here, not only is something being squared, but it's being squared in the denominator. And so that makes it very counterintuitive. Pretty straightforward once you get the hang of it, but you've got to practice it to get the hang of it. So we're gonna basically just use this equation and do what we call some factor of change stuff. Basically look at what would happen to our force if we changed one of the things about that equation. So regardless of what masses or what distances or anything like that we're using, if we double one of the masses, right? If I just take m1 and multiply it by 2, how is that going to change my weight or the force for this particular equation? We can go back and rewrite the whole thing. And the really nice thing about all of this is really all I'm doing is moving stuff around. We're doing old school freshman year algebraic manipulations. Remember, multiplication is cumulative. It doesn't matter if you do 3 multiplied by 5 multiplied by 1 or 1 multiplied by 3 multiplied by 5. You still get 15 no matter what order you do it in. So if we reorganize this to take the change that we made out front, what I've written here is the same thing as what I have off to the side, or let me highlight it. What I've written here is the same thing as what I had written here. I haven't written anything different. I reorganized where that 2 was, but because multiplication is cumulative, it's the same thing. And what you'll notice is that this is the original term for my force. So what I've done here is I've doubled it. I've doubled my force of gravity. I've doubled the weight of the object. If you double your mass, like you probably have since you were, it's 16 right now. Let's go back to, I don't know, when you were 8. in 4th grade. You have probably doubled your mass since then. I'm making things up. I don't know if that's how it actually worked. But for the sake of argument, you double your mass, you're going to double your weight. And that's exactly what we should have noticed, right? Now, if we double both of our masses, this is where it gets not complicated yet. Well, number 3 is where it gets more complicated. But you can do the exact same thing and see how your weight would change. So if for some reason you doubled your own weight and you doubled the weight or the mass, sorry, you doubled your mass, and for some reason you doubled the mass of the planet you were standing on, or maybe you got in a rocket ship and traveled to another planet that was twice as massive, and on the way there you got twice as massive, then you would wind up with a weight that is 4 times as great, right? Because it's the product of both of those two things. Now that should be pretty straightforward. The part that gets weird is when you change your radius, when you change the distance between the two objects. And it gets weird because it's in the denominator and it's being squared. So if we double your radius, if you hop in a rocket, and this is where Mr. Willis has omitted things to make life easy on you for the last month that we've been talking about Newton's laws. If you get in a rocket and you travel twice as far away from the center of the planet as you are now, ironically enough, you won't even get to the moon. That's how far our own moon is. I think the last figure I heard was you could actually fit all of the other planets in the solar system in between the Earth and the moon, and might have actually a little bit of space left to spare. It's really far away. It takes like 4 days to get there by rocket. Anyways, so if you get in a rocket and you double your distance away from the Earth, you've got to remember that not only is that radius being squared in that denominator, but any change you make to that radius is also being squared. You've got to distribute that square. It's the distributive property from algebra. It hasn't changed. It's just, we're 2 years later in physics, and now it's in the denominator, which is really weird. I'm going to do the same sort of thing I did before, right? So that 2 squared in the denominator becomes a 4, and the factor that I'm manipulating this whole thing by becomes 1/4. Right? If I'm going to go ahead and pull that out, I've still got r squared down there. If I'm going to go ahead and pull that 4 out, that 4 is in the denominator. And so what you actually wind up with is a weight that is 1/4 your original weight. So Mr. Willis, at about 200 pounds, if I said, this whole political climate is getting really weird, the coronavirus is annoying me, and I'm just going to leave. Peace out, guys. If I get twice as far away from the Earth, then I will no longer weigh 200 pounds. I'm actually going to drop down to a weight of 50 pounds, right? It's the best weight loss program that's out there. You just get further away from the Earth and your weight goes down, right? But that's the inverse square law, right? The force of attraction decreases by the square of the distance. That is the main idea. And that's the part that will trip everyone up, right? So if you double your distance, you get 1/4. If you triple your distance, you get 1/9. If you do 10 times the distance from the Earth that you currently are now, you'll get 1/100th of your weight. So it will never actually be 0, but you'll get so close to 0 that it's not worth calculating. Interesting, I guess you could say application of that whole idea. So, if the force of gravity, which obviously is going to cause an acceleration, why doesn't it bring things together? Why doesn't the Earth fall into the sun? Why doesn't the moon fall into the Earth? Why doesn't the International Space Station, with all those astronauts that SpaceX just sent something up to, why doesn't the whole thing come crashing down and burn up in the Earth's atmosphere? And it's got to do with something that we had to skip over in the last unit, but it is an idea called tangential velocity. Now this is just a regular velocity, right? But the idea is that it is the velocity that these objects have because they're traveling in a direction, or they want to continue to travel in a direction that is tangent to the path of the circle. So if this guy over here, let me get my red pen. If this guy over here was Earth, that little guy that I just colored red, if that was Earth and it's orbiting the sun, just like everything else is orbiting the sun, and let's say we just poof, made the sun disappear, the direction the Earth would continue moving once that gravitational force is gone, the thing making it do the circular path is gone, it's just going to continue flying in a straight line, right? Remember, that was Newton's first law. Newton's first law is that an object will continue moving at that speed and in that direction that it is currently moving forever, unless an outside force comes in to make it do something different, right? Forces it to do something different. And that force that is always causing it to turn is the force of gravity, exerted on it by the sun. And so that force of gravity exerted on it by the sun actually changes its direction and is what makes it go in the circular path. Kind of like if you were spinning your keys in a circle, right? If you take your long lanyard and you put your finger in it, and you start spinning it in circles, you've got to continually apply a force in order to get that the set of keys, the keys on the end of the string, to continually change direction. If you stop applying that force, it's going to stop moving in a circle. But that's what gravity here is doing. Gravity is forcing these planets or objects, asteroids, whatever they are, to go in circles around it. And the only reason the Earth doesn't fall into the sun is because it's got some measurable velocity where it's trying to move off to the left in this particular case, but the sun won't stop pulling on it. And it won't stop pulling on it, causing it to change direction again and again and again and again and again until the end of time, until the sun dies eventually, which will happen in about 5 billion years? Yeah, 5 billion. So if an object had enough tangential velocity or linear speed, they pretty much mean the same thing. I'm going to keep, just because we didn't have that unit, I'm going to keep using the same term. If it had enough tangential velocity and could keep it, meaning it wasn't bumping into anything else, then it's going to keep making that circular path. And one of the things that we can do, and the book spends a whole page doing this with you guys, which is why I am doing it with you real quick, so that you didn't have to work your way back to it. This was an equation that we would have used in our last unit, Unit 6, but we had to gloss over that one real quick. The main idea behind just showing you this, right? This is still F equals ma. This was the centripetal version acceleration, or version of our acceleration and calculation. Centripetal acceleration was your velocity squared divided by your radius, because your direction is what was changing, and so your radial vector was changing, and the equation got weird. Not the point. The point is, I have one equation that calculates centripetal force, and Newton provided us another equation that calculated weight, gravitational force. Well, if the sun is supplying that centripetal force to the Earth via gravity, these two things should be the same. They should calculate the exact same thing. And this is one of the things that we did. And this is where, time and time again, I told you guys that you're irrelevant. I didn't phrase it that way. I like to phrase it that way because it's funny. No one is irrelevant, especially emotionally. We love all you guys. But in terms of mass, in terms of the gravitational field that the Earth creates and generates, and the speed that you need to achieve in order to maintain orbit, your mass completely cancels out. Even one of the terms for radius cancel out as well, right? And so we can calculate how fast something needs to be moving to stay in orbit. That's literally what we're calculating here. This is our orbital velocity. The speed something needs to be traveling at, again, velocity measured in meters per second, to maintain orbit, to not fall into the planet or to not go flying away from the planet. Too much orbital velocity and you drift away into the cold, dark, empty recesses of space all alone for eternity. Too little orbital velocity and you crash and burn in the atmosphere of the planet. That is the balancing act that the International Space Station and every satellite we've ever sent up into space is currently doing. You've got to maintain that ideal orbital velocity based on your radius, right? Your distance away from the center of the planet measured in meters, based on the mass of the larger object, right? Because the mass of the smaller object disappeared. So it doesn't matter how big or small that satellite is. We can keep adding pieces after pieces after pieces onto the International Space Station. We could make it as large as Well, right now it's about the size of a football field. We can make it the size of the entire school of Lincoln Way West, and it won't change its orbital velocity because the gravitational field it's orbiting in is established by the Earth, and the Earth is a lot bigger. And then this is the, again, universal gravitation constant, and that value still has not changed. It is still units of a Newton meter squared per kilogram squared, and you'll notice that we're taking the square root of the whole thing there at the end, and so your units are literally just going to wind up being meters per second when all said and done. So the book spent almost an entire page going over that entire thing, but the main idea is that you've got to have that orbital speed. That orbital speed is based on these. I wanted to give you the equation, or sorry, the steps to that equation, so that you knew Mr. Willis wasn't just making things up for you, kind of like before. I always, pulled an equation from a graph, and I said, all right, well, if this is the, our y-axis and our x-axis, then this would be our slope, and these are what labels went on the y value and the x value, and we were able to figure it out that way. Interesting, or sorry, that is the equation that we'll use to calculate the speed any object needs to travel at in order to orbit it, in order to orbit whatever bigger object it is. And this is actually something that Newton did way back in the day, like 400 years ago, because that dude was kind of smart. This was his drawing. This is his schematic. This came from his book, Mathematica Principia, way back then. He was postulating that it is possible to get something to travel around the Earth. His idea was, let's look at a basic projectile. The more horizontal velocity we give it, the more horizontal distance it can cover each second. Right? Gravity's going to pull it back down to the ground every single time. There's nothing we can do about that. But if we increase the horizontal speed enough, you can cover enough horizontal distance each second. And that's actually what the International Space Station is doing. They're not weightless up there at the International Space Station. They're just traveling in circles around the planet fast enough to where the horizontal distance they cover is the same as the curvature of the planet. So every second that they're falling, they fall the same, they basically fall around the planet, right? And they're just perpetually falling around the planet again and again and again and again. So it looks like they're weightless. They're really not weightless. They're just in a state of perpetual free fall, right? They're just always falling. That's it. And so that was your, International Space Station, Newton, a couple hundred years ago, telling us exactly how to get something in orbit around the planet. And then it took until, 1950s for us to actually pull it off. So we can go a step further using that same equation and actually calculating the orbital period. This is a lot more complicated, but again, this equation right here was actually our original equation for linear speed, or tangential velocity, and if we're using the equation from up above, because that's where that came from, for tangential velocity, we could set both those equal to each other and basically solve for t. Solve for your period, the amount of time that it's going to take for the Earth, orbital period. That is one of your vocab terms from the book, so you need to know what a period is. A period is just the time for one. The official term they use is cycle. I'm going to call it trip. Time for one trip all the way around, right? One loop, one lap, however you want to describe that. It's the amount of time it would take, or the period, for that object to make one trip around the planet. And this is where I did the rearrangement, right? To get rid of the square root, you've got to square both sides, which is where these squares come from right here, because we get rid of that square root. And then we cross multiply some stuff and divide both sides by your universal gravitation constant and the mass of the planet Earth. And bada bing, bada boom, there's your equation for orbital period. Now, you're not going to ever have to derive it. Don't worry about it. What's in that box, that's what you should have on your equation card. That's what's on the front of the unit packet. That's what you're going to need to know. Where it's derived from? No, I wanted to show you the steps so you knew I wasn't making it up for you. But those are some of the things we can do. So, how does all of this tie into what we already know, right? If you recall back a couple of units, we watched the bowling balls and the feathers both hit the ground at the exact same time. We watched the Mythbusters video where the bullet fired and the bullet dropped. Both hit the ground at the exact same time. There's only one possible explanation for how all of those things could happen, and that is that the Earth determines how quickly things fall, and nothing else matters, right? The Earth is the one common thing that they all have, and the same. The bowling ball and the feathers and the two bullets, they're moving with different speeds. They have different masses. They have different surface areas, different densities. So how is it that in that vacuum chamber, or in the case of the two bullets with the two different speeds, how is it that they're able to hit the ground at the exact same time? And that the only logical explanation is that the Earth is doing the same thing to all of those objects. That's it, right? If you remove the air, or if you get rid of any potential angle that bullet fired could be traveling at, there has got to be some explanation for why the Earth does this. So Newton's law of universal gravitation gave us a new way to calculate weight. Well, we already had an old way to calculate weight, right? We had F equals ma. This was Newton's second law. Newton's second law, now we have Newton's universal law of gravitation. Those two things should be equal to one another. And this is one of the things that he was able to do. This is where we got this value from. Interestingly enough, when they finally worked out the mathematics for this, there were headlines all around the world where it literally stated, you can Google this, scientists discover the mass of the Earth. This was the first mathematical, they had estimations, but this was the first mathematical equation that we had that consistently defined the mass of the Earth at the value that we know it to be now, right? And so it was pretty cool. But it comes from taking our old way of calculating weight and setting it equal to our new way of calculating weight. What you'll notice, like I've said before, is that the mass of the smaller object, in this case u, disappears completely. And if you wanted to calculate the acceleration due to gravity on the Earth, little g, right, -10, or what should be 9.8, we can calculate reliably with this, right? Your radius would be how far are you from the center of the planet. So literally, what is your radius on the crust of the planet to the core, to the center, and then the mass of the planet goes on top. Your mass cancels out because it shows up in both of those equations, just like it did for finding the orbital speed of that satellite. So there's a common theme here with all of our equations. If you have to guess which mass to use, always go with the larger of the two objects, right? It's always the bigger mass. The reason that it works out this way is that the Earth is actually generating what we call a gravitational field. And the ideas of fields are weird, and it's kind of the newest, I don't want to say newest, it's not the newest, but it was in the early 1900s a big revolutionary change for how we view the world in physics in general, is that there are these invisible fields that are connecting things either through magnetism or electrostatics or gravity, where they don't have to be in contact with one another, but they can still exert forces on each other through these invisible fields that we can't see. But we know they exist because we can observe things following the lines of those fields all the time. If we go all the way back up to the very beginning, the very first thing we had here, the reason the apple falls down is because it's following those gravitational field lines that the Earth generates as it tries to pull all things towards its center. And that's it. It was actually people were laughed at. The first couple of scientists who proposed fields, electric, magnetic, or gravitational fields, they were laughed at because it was a really cool idea. They referred to it as hand waving, but there was no math to back it up. And it took, who was it, Maxwell? James Clerk Maxwell, I think it was, and a few others, to figure out the mathematics for how these fields should work. And then Einstein took it and ran with it and gave us all of these crazy ideas that over the last 100 years, pretty well supported now, even though they were really weird at the very beginning. But that's how we're able to calculate the gravitational field strength. That's what we refer to it as, or the acceleration due to gravity on the Earth, right? So we also call this value, and this is what I'm going to call it here from here on out, acceleration due to gravity, or the gravitational, gravitational field strength. Gravitational field strength. So, yeah, so this new equation demonstrates why the bowling ball and the feather and the bullet fired and the bullet dropped and all of those things all acted the same way, right? It's the Earth's gravitational field, which doesn't care about the smaller object moving in that field. It's a field that is established by the mass of the planet and how far you happen to be away from that planet or from the center of that object. The center of that object's mass, right? The individual object's masses all cancel out. And the small mass, basically becomes irrelevant. The gravitational field strength is established by the mass of the planet, the mass of the larger thing. In other words, and this is the part I like to say, your mass is irrelevant. It's just more fun to say that. But that's the mathematical explanation as to why. And that's how this unit was going to get started. So those are probably three, and that's why I started with it, three of the more complicated equations that the book presents in this particular chapter. And I wanted to walk you through where it gets those and why we use them the way that we do. So for the next part of this, as we progress into the later parts of the semester, or really just the end of the semester with this last unit, we're going to spend the next couple of days working on a lab. I'm going to modify the lab a little bit before we get too far into all of this, cut it down a little bit. We might not need 2 days, and if we don't, then I'm definitely going to spend extra time going over assignment 2 with Kepler stuff. But all of the Kepler stuff is coming straight from the book, and so it's all there. Obviously, ask any sort of questions that you guys have over the next couple of days for sure. But this is mostly a conceptual worksheet. There's very, very, very little math, and it all comes straight from the book. There's a couple of math problems right there, obviously, but most of it is going to be using Kepler's laws in some way, shape, or form. So that's about it. We're going to take off from there, and if you've got questions, comments, or concerns, don't hesitate to let me know.